Okay. Okay. So, hi everybody. My name is Jarek Korbicz. I'm from Center for Theoretical Physics of Polish Academy of Sciences in Warsaw. And first of all, I would like to cordially thank Tao and the rest of the organizers for inviting me for this workshop. It's a very nice event, gathering people working on objectivity, quantum Darwinism, and related issues, which I've been enjoying a lot. So big thanks again. I will present today a alternative to what we have heard approach to quantum Darwinism. The title of my talk is Objectivity in and from Quantum Mechanics, in the sense that I will try to show you how objectivity is encoded in quantum mechanics, or how it can be extracted from quantum mechanics in a sort of a quantum to classical transition. Let me begin with the plan. Maybe we've heard a lot of definitions of the problem of objectivity and motivational talking. So I will just briefly touch the subject. I will then discuss the first attempt in quantum Darwinism, or more precisely the entropic condition. Then I will show what we have come up with, namely special states called spectrum broadcast structures. I will probably then not have much more time than just go quickly through appearance of spectrum broadcast structures in models. I will touch typicality in measurements and conclude with some remarks. So we've heard already what is the main problem, namely, if quantum mechanics is to be the most fundamental theory that we have about nature, then how come that what we observe is, or at least seems to be, objective, while in quantum mechanics we know that every act of observation in general disturbs the observed object. So there is no sense to talk about objectivity, at least how we understand it. So we need to build some sort of a bridge between one and the other. And this is, of course, a aspect of the celebrated quantum to classical transition. One of the aspects which was actually noted, to my best knowledge, by only very recently, so some 20 plus years ago, by Wojtek Żurek and then collaborators, Michael Zwolak, Jess Riddle, Robin Blume-Kohut, and the rest of the first pioneers, so to say. It's very strange that it has been neglected for such a long time. Okay, what is objectivity? We've heard today a lot of different definitions, and talking basically it has something to do with let's say truth and reality, how philosophers define it. There is an interesting perhaps aspect here, the geometric objectivity, namely the frame invariance, the possibility that we see the same object but from a different point of view. This has not been discussed so far, as I understand. In all the objectivity studies I'm aware of, we want to see exactly the same object. Well, we can have this little freedom and say, okay, we see the same object but from a different point of view. I think this is a nice thing to think about. But among all possible aspects and definitions of objectivity, I will concentrate on one operational definition, which was written by Wojtek Żurek in his seminal paper from 2009 on quantum Darwinism. It was written, I think, a bit as a byproduct, as something to more specific to have in front of your eyes, but we took it seriously. Namely, the definition states that a state of a system exists objectively if many observers can find it out independently and without perturbing it. However simple it sounds, you will see that it has actually quite non-trivial consequences. What I wanted to stress here is that intuitively, objectivity is a agreement. So many see the same, and non-disturbance. So they see it without disturbing it and without disturbing each other. These are two basic constituents of objectivity: agreement and non-disturbance. Okay, so also it is also, I think, good to keep in mind that the objectivity we have been talking about here is the objectivity of a state. It's not objectivity of ontological, so to say, of a system, whether the system exists or not. If we don't observe it, we don't go into all those deep philosophical questions. It's a question about objectivity of a state of a system. So the ability to observe the state of the system independently and without perturbation. And of course, the question is how this can happen. While we know that in quantum mechanics, basically every act of observation is disturbing the system. Now, the first attempt is the quantum Darwinism. What I mean here is not so much the idea, but the proposed test for observing when objectivity happens. So that's why there is this entropic added in the parentheses. The quantum Darwinism setup, we have heard that already, but let me repeat that the objectivity reformulated maybe slightly is equivalent to the information redundancy and non-disturbance. And of course, this is information redundancy. This information is not only has to be redundantly encoded, but in principle should be extractable, and this extraction should go without disturbance to anything, to any of the players. This we've already heard, that the environment can store information, and actually majority, if not all, human observation are indirect, so the seeing, but also hearing. It's mediated via waves in the air. The basic setup remains as it has been in the previous talk. So we have a central system of interest. The system interacts with its environment, and the environment is treated quantum mechanically, and it's not as usually in quantum open system textbooks, the treatment of environment is like a big chunk of something. No, it is not. When you think a little bit, what we usually treat as environment is some huge collection of degrees of freedom over which we have poor or in many cases no control. So environment is structured. It consists of its own subsystem or its own modes. And the absolutely crucial step that has been made by Wojtek Żurek and collaborators is that some parts of the environment are assumed to be under observation. Yes, this is our source of indirect. This is our indirect source of information about the system. Okay. This seems like a little change compared to, let's say, textbook open system quantum mechanics, but actually the change is quite deep, because it turns out that, well, a natural consequence is that we cannot trace all of the environment. Since we want to observe parts of it, it has to be left in our description, and this actually changed the whole picture. So consequently, our main object of study is what we call a partially traced state. Well, partially because we trace out only the unobserved part of the environment, leaving parts under observation. This has to do with a natural loss of environments in all realistic situations. Of course, you cannot imagine, for example, capturing all photons that scatter, let's say, off my face in all possible directions and in all possible frequencies. What we see is just some solid angle and some part of the electromagnetic spectrum, while the rest just disappears, is out of our control. So we can trace it out. Yeah, and we can view this approach, this quantum Darwinism approach, we can view it as a more realistic and refined form of decoherence, with the main accent here on the fact that environment does store information about the system. It's not only source of noise, as it has been treated for 40 years, if not more. Okay, so that was the main setup, and well, the question remains how to recognize if the redundancy and non-disturbance have happened. So how to recognize that we deal with a situation where the state of the central system, so the state of this guy, has become objective, that the information about this state has proliferated in the environment during the interaction. Okay, we need some sort of a witness, for example. It's language from entanglement theory. We need some sort of condition which will tell us that this has happened, that this state has become objective. And the first and the most popular proposal is to look at the quantum mutual information between the system and the fragments of the environment, and compare it with the entropy, von Neumann entropy of the system alone. So when we trace out completely the environment, and then the postulated objectivity happens when the mutual information, as a function of the fraction size, reaches a value of the system's von Neumann entropy, and stays for some time, for some increasing fraction size. Well, we have seen this condition many times. The problem is that this condition is perfectly fine in classical information theory. At least the part of this condition which says that if we add new subsystems, the mutual information stays the same, because the condition that the mutual information is equal to the entropy of one of the subsystems in classical mechanics is already too strong. It basically says that these two random variables are deterministically connected. While the condition that we add new sub-environments and the mutual information stays the same, in classical mechanics, this is a beautiful condition which almost immediately leads to the fact that the old and new environment, so the one that we have added, has to be deterministically related with the environment which was already there. In other sense, in other language, adding new environment does not bring any new information about the system. Okay, this is perfectly and quite easily shown in classical information. However, it is absolutely non-trivial in quantum mechanics. And the point here is there are several aspects, like several problems with this condition as a test for quantum Darwinism. I will understand quantum Darwinism not as much as the entropic condition, but I will understand quantum Darwinism as the whole idea that we have during the interaction with the environment, we have a proliferation or redundant proliferation of information. This information is in principle extractable from the parts of the environment without disturbance. This is what I will understand as quantum Darwinism. So that's the main concept, and now there are the tests. When does this happen? Okay. So what I'm criticizing here, I'm criticizing the entropic condition. That at least looking from the first principles, it is absolutely not so that while adding new environments and keeping the quantum mutual information constant, we can prove, just like we do it in classical information theory, we can prove that the new environment does not add any new information. Okay, what we can prove is actually this is a very difficult mathematical theorem. It's called quantum Markov states. We can prove that there is some property, there appears some sort of a classical property in such situation when the quantum mutual information stays constant when we keep adding subsystems. But this information is not necessarily what we want. So it's not necessarily the information about the state of the central system. Okay. Perhaps this is, now it's a pure speculation, but perhaps this is related to the fact that the operational meaning that we have of a quantum mutual, not classical, but the quantum mutual information is quite different from what we have in a classical information theory, namely quantum mutual information, how it is defined operationally, it has to do rather with destruction of correlations rather than with building correlation. It's the asymptotic amount of random noise that we have to add in order to split any bipartite state into a direct product of its one-partite reductions. It's one of the operational definitions. So the bottom line is that we read and we hear all this beautiful talking about classicality plateau, and that it leads to the redundant information proliferation, and that this information can be in principle extracted from the environment. That's great, that's fine. But what we did, we asked the question, okay, so how do you do it? How do you extract it? Okay, and it turns out that at least how it is formulated on the, so to say, abstract level, quantum mutual information and this entropic condition used to check for objectivity, it seems that it has to, it is too broad. It allows for too much. So one of the aspects, for example, is that in principle it can allow for discord. So it can allow for correlations which are non-locally extractable, and what's more importantly, the extraction the local extraction of information under the presence of discord in general leads to disturbance. This has been shown very nicely in the paper of Tao and Alexandra in 2019. I also analyzed it in a lengthy paper dedicated to objectivity. But the bottom line was that it looks like it's a very nice, appealing condition, perfectly fine in classical information science, but not so obvious. I mean, there is no direct implication from the entropic condition to a measurability existence of preferred measurements which allow you to extract the right information, the same for all the observers and without disturbing of the system, or at least we could not see it. Okay, so that motivated a new approach and a revision of how to test for quantum Darwinism, so how to say when this objectivity happens. And this is what brings to us to the spectrum broadcast structures. The idea is to take the Wojtek's definition of an objectivity and try to formalize it. Try to go step by step through this definition and well, try to see where it leads to. Okay, so as you see, there is quite a lot of wording here, like from a physical point of view. For example, one of the key words is perturbation. So what does it mean not to perturb? We know that this problem has been at the core of quantum mechanics from its very birth. The whole Bohr EPR, the famous Bohr EPR debate on the completeness of quantum mechanics from 1935, it revolves somehow around the problem of disturbance and non-disturbance. It's actually quite funny that here we will use Bohr's definition of non-disturbance, which at the time Bohr used to save quantum mechanics from the EPR, let's say, attack. So he used it to defend quantum, and here we will use it to define classical, so to define objectivity. So as a non-disturbance condition, we will take probably the strongest form of non-disturbance, namely that, of course, expressed in the modern language, there exists a non-demolition measurement which leaves the whole partially traced system unchanged. This is the system. This is the state of the central system of interest and the part of the environment that is under observation. Okay, this is one of the key ingredients into making this loose, but still with a nice operational flavor definition into a concrete and precise structure. The second condition, which is actually a bit technical, as for example Tao and Alexandra showed later, is the condition that the only correlation between the environments is the common information about the system. I must say, like I have to admit that we added it just to have the structure which at the time we were seeing in the models, but and it's also easier to work with these structures, but for objectivity itself we can neglect it. Okay, so well, there are maybe before I come here, so there are a few more things which have to be specified, namely what does it mean to find out? Well, to find out, we interpret as performing von Neumann measurements. Von Neumann, because they are the most informative. Independently, well, the von Neumann measurements are product measurements, so there is no correlation between the measurements at all whatsoever. So when we take all that together, when we agree that this Bohr non-disturbance is the way to go here, because it's the strongest form, quite surprisingly, all that leads to a basically unique multipartite quantum state structure. This was a big surprise, that taking a definition which was loosely written by Wojtek in his seminal review of Darwinism, if you treat it, if you try to formalize it using quantum mechanical concepts, then you can prove a sort of a theorem that the only state structure which is compatible is the following. Namely, it's as you see, from the point of view of quantum correlations, the state is as boring as it can be. It's a completely classical, whatever classical state. These are the usual pointer states. So if not this tail of environments here, that would look like a abstractly written state after decoherence. These are PIs, are the probabilities of the pointers, the initial probabilities of the pointers. Now, these states here are the states of the environmental fractions, so the subsystems of the environment, which we've left for observation. Yeah? You remember that the basic setup was the system plus part of its environment, which is under observation. Okay. And these states, the important thing is that these states are enumerated with the index I, the same index that enumerates the pointer states, so the states in which the system is. Okay, and now for people who are wondering what kind of information I'm talking about, what is this mythical information? Now you can see it very clearly. Now you can see it written in black and white, or actually here in gold and blue, that this is a classical information. And this is a index which identifies the pointer state. Okay, and this classical index, it's present in all the fractions of the environment. There is no bound on how many fractions they can be. So this is this redundant proliferation of information. And the environmental states, they have this property that for different indices, for different, they are enumerated by the pointer states. For different pointer states, they have orthogonal support. So every eigenvector of this guy is orthogonal to every eigenvector of that guy. What this means from the operational point of view, and namely these states are one-shot perfectly distinguishable. Okay, so we can construct a measurement, and it's very easy to guess what is this measurement. This is a projection on the range of each of the operators for different i's, which will tell with which state we are dealing. So this will allow us to identify the state in which the central system is. More, so I have here the first thing. Okay, I have shown that there is an agreement. So I have a state structure which shows the agreement. Whoever measures, including some super observer who can access the central system, so the system of interest directly, whoever measures in whatever configuration, so some observers can measure, some observers will do nothing. But if we use if we ask the right question, so if we use the right measurement, all of the observers will see the same result I. Okay, the probability that different observers see different results is strictly zero. Of course, this state structure is some sort of an ideal. In concrete models, we can approach it, but I'm showing you an idealized state. This is like a limiting case where to go. Then it is also easy to check that if we take the post-measurement states, so we've done the information extraction, we applied the measurement, we obtained some results, with some probabilities, some post-measurement states. If we forget the results, so this is called sometimes non-selective measurement. If we forget the results, if we average all over the results, we will reproduce the same state. Okay, so in other words, these measurements adapted to the structure, or actually the measurements that come from the definition, they are non-demolition. So we have non-disturbance in the in the strongest sense of Bohr. Tao, how much time do I have?
You have about 6 minutes.
6 minutes.
Yeah, and then after that, questions.
Okay. So this structure is a stronger. This is a strictly stronger condition than the entropic condition used previously for checking for objectivity. One can very easily prove that from this structure with this property, one proves the entropic condition of quantum Darwinism. Implication in the other direction is actually a very hard mathematical problem, and this is a one big result by Tao and Alexandra from 2019. Namely, they identified what else has to be added here in order to come here. Okay, and it turns out that actually pretty strong additional constraints have to be added in order to get those spectrum broadcast structures. So this structure which we derive directly from the definition of objectivity. Well, one of the most exciting things here is that the notion of objectivity, sort of a philosophical notion, becomes directly translated into the structure of quantum states. This is a very exciting point here. Now, the hard part, okay, that was all very sweet and romantic, but now comes the hard part, how to check for them. And checking for SBS state is much harder than checking for entropic condition of quantum Darwinism, for checking for quantum mutual information, because basically one has to solve the model with the environment, with a part of the environment, and see if you approach this SBS state or not. And this is difficult because there are no tools. All the tools that you have in open quantum systems, they deal with the situation. You have environment, interact, forget all of the environment, and then you are interested only in the central system. Okay, and all this the Born, Markov approximations, master equations, GKLS, or whatever, this is all adapted to one goal: study of the central system state alone. There are no tools to study more than just the central system, so a part of the environment. We had to do it just like model by model, really hard work in order to extract this spectrum broadcast structure. So I suppose I have now about maybe only 2 or 3 minutes. So I will go very quickly through the models that we studied. First of all, the iconic model that appeared already today, the illuminated sphere from 1985, model traversed there and back for years and years, and we were still able to show that there is something new to be said about this model, namely that there is an asymptotic formation of SBS states. Spin-spin models, which also appeared today, they also show in this simple scenario where the interaction dominates, they also show pairs of SBS states. These are these points, these black plateaus here. The green is the green plot is the decoherence, and this colored one is the so-called orthogonalization. It's a check, it's a test for 2 states having orthogonal supports. We are using with generalized fidelity to check for it. So spin register, which leads to a sort of a coarse-grained structures, spectrum broadcast structures, where instead of pointer states we have pointer subspaces, and their index gets proliferated. Spin boson model, where we studied if there is any connection between SBS and non-Markovianity. In this model, we did not find any. Very difficult from this point of view model of quantum Brownian motion because of the self-Hamiltonians, but still in some simple regime, we were able to show SBS formation. Quite a funny study, universal gravitational decoherence of Pikowski and the co-authors. There is also SBS, sort of SBS formation. Now this I will skip, and perhaps one of the nicest results is that we were able to prove that for this type of Hamiltonian, so pure dephasing, there are different names for them, pure dephasing or generalized measurement. This is a generalized measurement Hamiltonian. We were able to prove a form of typicality of SBS state for this type of interactions. Okay, there is still some work to be done, but basically what we were able to show is that when we draw the observables which constitute the measurement or the interaction from a random ensembles, then the average distance from the actual partially traced state to the nearest SBS state with the size of the fragments that we are considering, it goes to 0. So the state approaches SBS. So when the apparatus is macroscopically coarse-grained, and we went long enough. Very nice result due to Carlo Scandolo and Roberto Salazar, myself and Paweł Chorodecki, is that SBS actually, the structures are more general than quantum mechanical. You can prove them in a wide class of generalized probabilistic theories. This article actually has been published in physical research, physical review research. I forgot to add the reference. Now there are still a lot of things to be done. For example, objective motion. That's an interesting question. So far, I have been discussing, and we have been seeing in the talks, objectification of static properties, but how to make objective, like I'm waving right now, how to describe objective motions. There are already some quantum Darwinistic works, at least one work with decoherent history, with consistent history. I'm wondering how to describe using the SBS. Big question. So are SBS, are the structures notoriously formed in real life situations? The big sort of speculation, the big hypothesis is that we perceive word as objective because of some sort of a illusion. Because in macroscopic situations, these SBS structures, so these structures encoding information, are notoriously produced, and this typicality result for pure dephasing or generalized measurement Hamiltonians. This is like one small step in that direction, showing that for a very important class of interactions, SBS states are typical if you coarse-grain your measuring apparatus or your environment enough. Also, there is another interesting question. So we've observed all these objectivity properties, like well, the formation of SBS. We have to take some sort of macroscopic limit somewhere in some form. A lot of spins, large mass, thermodynamic limit. It depends on the model. But the interesting question posed by Professor Rzążewski is that perhaps objectivity is at all a macroscopic property, that it appears only in some sort of a macroscopic limit. This, of course, corresponds to the previous question or hypothesis that objectivity is some sort of illusion, because we have these SBS structures, and they give us what our brain interprets as objectivity. Okay, and the people who were or are involved in the project, and big thank you, and I'm sorry if I spoken too long.
That's fine. Okay, thank you, Jarek, for your talk. Yeah, it's really nice to see SBS instead of just soft quantum Darwinism. Okay, Akram has a question. You want to go?
Yeah. Hi. Yeah. Thanks for the talk. So, I just have a more general conceptual question. So, the framework of Darwinism is really built on this idea of redundancy, which on itself is defined through an information deficit, and this is kind of imposed on us by realistic assumptions, such that the plateau is really reached for the mutual information only when you have half fragments of the environment, when you access half of the environment. But realistically, you should allow for some information deficit, which doesn't seem to be the case in the definition of the SBS. So I'm really curious about whether were there attempts to formulate a spectrum broadcast structure, but allowing for an information deficit, but not talking strictly about the plateau. Because at the end of the day, we are somewhere near the plateau, but we're definitely not in a plateau in realistic scenarios.
Yes, of course, and I think I mentioned it, but maybe not hard enough. So this is an idealistic structure.
Yeah.
This is an idealistic structure, but what we see in reality, we never see a perfect decoherence. So there will be always some sort of a coherent part, albeit small, and we never see a perfect orthogonalization. Both these two things, especially non-perfect orthogonalization, this is more difficult condition to get, and this can be proven actually, and it takes longer time usually than equivalent decoherence. When there is a coherent part present and when there is a non-perfect orthogonalization, then you don't have all of the information perfectly available, plus you risk a chance of disturbance.
Yeah.
Especially the non-vanishing coherences will open the gate for disturbances.
Yeah.
While non-perfect orthogonalization will give you non-perfect information extraction.
Oh, okay. Oh, I see. Yeah, thank you.
Okay, we should actually go to the break now. I know that Michael still has a question and Ajay has a question, and you guys can continue talking in the breakout room. Yeah. So, yeah, thank you again to Jarek for your talk.
Thank you very much.